So we're going to be talking about exponential growth and decay and what that kind of looks like when it comes to differentiation and integration and all that kind of stuff right there. So the first thing we're going to talk about are called separable differential equations. Okay. Okay. So that's the first thing we're going to be talking about. And so what exactly are those? Okay. So here's our definition, right? Okay. So our definition. Equations of the form dy over dx equals fy gy, okay, or excuse me, fy gx, excuse me, so you'll notice that they are different variables, okay, is called separable Okay, so you'll notice that dy dx, f of y, g of x, right? We separate the variables by forming it like this. So 1 over fy dy is equal to g of x dx. Okay. Now, you're probably wondering how that is and what that means. Okay. So again, our definition, our equations of the form dy over dx is equal to fy times g of x is called separable. So we can write, I'll write it like this. So we can write 1 over fy dy is equal to gx dx. Okay, so why is that? Okay, so what happens is if we look at it like this, dy, I'll write it in different colors so maybe it makes more sense, dx is equal to fy g of x, right? And so what we can do is we want to get everything in terms of y, we can get together, and everything in x we can get together as well. So what we're going to do essentially is I'm going to move the dx to the other side. Okay, so I multiply both sides by dx. Okay, all right, and so then those cancel out. Then, so really I'm saying dy is equal to fy times gx dx, right? And then I want to divide both sides by f of y, right? Okay, and so then those cancel out. And so I end up getting this, 1 over f of y dy is equal to g of x dx, which is what we just said. They're considered separable if this is the case right here, okay? So what we're going to do is we're going to look at this in the form of an example, okay? So here's our example 1. Okay, it says solve for y So we're asked to solve for y if y dx equals xy squared, and we know, and we're looking at it, and y equals 1, x equals 1. Okay, so so basically what we're asked to do is we find out what this is, right? Okay, so we're going to say dy dx, okay, our derivative is really going to be, well, we write it as x squared y squared, right? Because if you're taking x times xy times xy, okay, it's going to be x squared y squared, right? And so if I say, okay, this right here is going to be like our g of x, and this right here is going to be like our f of y, right? I can go back into my separable and how I write it, and I would write it like this. I'd write it as 1 over y squared dy is going to be equal to x squared dx, right? All right, so if we just write it like this on our definition, that's how we would say it, okay? Now, the thing is this right here, okay? So what we're going to do here, I guess, let me say it this way, I guess, okay, is I'm going to differentiate both sides, right? Because I have my derivatives, it means I'm going to differentiate, right? And so we said, okay, well, when you take the integral of 1 over y squared, right, it's really like y to the negative 2, okay? So I'm going to say it's really the same as this, y to the negative 2 dy, okay? And then is equal to x squared dx, right? We know how to do this. We know how to take the differentiation. Remember, we add 1 to our power, so plus 1 would be y to the negative 1 divided by the new power, right? Plus some constant is equal to, let's see, x to the third divided by 3 plus some constant, right? And so we're not quite sure what that constant is at this point. In fact, the book tells us that this doesn't have a constant, and that's fine. We don't have to worry about it, right? And so what we're going to do is we're going to do this. We're going to say, okay, well, if we know that this is differentiated out, right, we want to figure out what C is. And we can do that. We can actually do that by plugging in the numbers that we know, right? So we know that x is 1 and y is 1, right? And so we're going to plug those numbers in specifically, and we're going to say, okay, so this is going to be 1 to the negative 1 power over negative 1 is equal to 1 to the third power over 3 plus c. And so then you end up finding out that this is just going to be negative 1, obviously, and this is going to be 1/3 plus c. So if I solve for c, I do that by subtracting 1/3, I subtract 1/3, and I find out that c is negative 4/3, right? Negative 1 and 1/3. So what that means is that negative y to the negative 1 power, right, is really equal to x to the third over 3 minus 4 over 3. Okay? Now, we have to solve this for y. And right now, we have y to the negative 1 power. It's not solved yet, right? So what we have to do is we have to get that so it's not really 1 over y, right? And we've done this before. If you say 1 over y is equal to 2 over x, then y is equal to its reciprocal. We flip it, it'll be x over 2, right? So the same is going to happen right here, but we're going to do a little bit of goofy math. Not really goofy, but a little bit. So we're going to say that this is, first off, I want to get rid of the negative sign, right? So I'm going to multiply everything by negative 1, right? Multiply by negative 1. And so what ends up happening is this becomes positive. So I get 1 over y is equal to, let's see, negative x to the third. And then negative would be positive 4. And then you'll notice they're both over 3. So I'm just going to write it as one thing right here, right? And so what I can do then, if I know that 1 over y is equal to that, I'm just going to flip it. I'm going to say y is equal to 3 over negative x to the third plus 4. There's my problem right there. That's my differential equation right there. Okay? And so now what I could do is I could actually put in any value of x and y and figure out what it is, right? But we're not going to do that for right now. This instead is our function in terms of y. Okay, so if we know that we have some dy over dx is xy, right? What I can do is I can actually end up just figuring out what our original problem is, our original function, which is 3 over negative x to the third plus 4. Okay? Okay, so law of exponential change is the next thing we're going to talk about. Okay, law of exponential change. That's what we're going to be talking about right there. Okay, so here's the definition, right? Definition. Okay, so our definition says this. if y changes at a rate proportional to the amount present, meaning if dy of dt equals ky, then y is equal to y naught when t equals 0. Okay, so what does that really mean? Okay, it means this. If, I'll just rewrite what I just said. If y changes at a proportional rate to the amount present, okay, if y equals y0 when t equals 0, then you get this formula right here. Y equals y0 e to the k t power. And you've seen this this exponential growth problem before. You've seen these before all the time. Remember, if k is bigger than 0, we call it exponential growth. If k is less than 0, we call it decay. So remember, k greater than 0 is growth. K less than 0 is decay, right? And so again, this is how scientists use carbon dating to figure out the age of a fossil or something like that. They say how much carbon was present at a time, and then we can figure out how old something is, right? And so that's our exponential change, right? Now there is a problem that says, what if A is, or what if we're looking for compound interest? That's another way that we can look at this as well. It's kind of the same idea, right? We use this formula right here for compound interest. Right, compound interest problem is going to be the amount at time t is going to be equal to our principal e to the rate times t. We call this the PERT problem, right? You've seen it before. It looks like it spells PERT, P-E-R-T, PERT, right? And so this is continuous compound, right? So obviously P is our principal, E, and then R is our rate, T is our time, right? Okay, and that's important right there. Okay, so we're just going to look at one more example right here then, okay? And so what we're going to do is we're going to say example 2 is this. We're looking for compound interest, right? It says, suppose you deposit $800, okay, in an account that pays 6.3% interest, okay? How much do you have after 8 years? So we're going to look at it a couple different ways, okay? So we're going to say how much after 8 years compounded continuously. And part B is how much is the 8 years compounded quarterly, okay? Now what's the difference? Okay, obviously compounded continuously means that it's compounding all the time, right? And compounded quarterly means that it's changing, we're only compounding it 4 times a year, right? Okay, so this is the 2 different types of problems, okay? So part A, right, wrote it in blue, I'll answer it in blue. We're going to use our PERT problem. So A of 8 is going to be the original amount, $800, e to the 0.063. Notice I had to change my rate into a decimal, times 8 years, right? And I go to my calculator, right? I type this in, and I get 800 e to the 0.063 times 8 power, and I end up getting 1,324.26. That's how much is in if we compound it continuously, right? Now in part B though, we're going to compound it quarterly, right? And so that's a different problem all in itself, right? And so for that one, maybe you forgot the formula, but we'll write it out. It goes like this: A of t is equal to P times 1 plus R over N to the N times T power. And the reason we use that one is because now we're taking our rate divided by how many times it's compounded, and then it does it N times T times, right? So for us, we're going to say A of 8 is equal to 800 times 1 plus 0.063 over 4 times to the 4 times 8 power, right? And so when I put this in my calculator, I end up getting 1,319.07. So you'll see which one yields more money. Now, $5 doesn't seem like a lot, right? But think about this happening for a long, long time, right? Think about that for a long, long time. Or for example, your mortgage is a 30-year mortgage generally. And so think about it. Over 8 years, it costs you an extra $25, right? Or $5, excuse me, over 8 years. But now make that instead of $830, it's be a lot more money, okay? And so that's how the banks make more money on our mortgages. They do continuous compounding. They don't do it quarterly. They don't do it monthly. They do it all the time, right? And so that's how we do it. And so that's what we're going to be talking about here for compound interest. The last thing we want to talk about, we talked a little bit more about it, but we're going to be talking about radioactivity, which is we talk about radioactive decay, right? And so that's, again, how carbon dating happens, right? One of the things we talk about is called half-life, and that's when you get half of what you originally had, right? Okay, so what we're going to do is we're going to be looking at an example, right? Here's an example, and we're going to be talking about, we'll call this half-life. This is the half-life problem. Okay, half-life. It says, find the half-life of a radioactive substance with the K equation Y equals Y0 e to the negative KT power, and show that half-life depends only on K. Okay? So, here's what we're going to do, okay? So, we know that it only depends on K, right? So, we want our original amount, e to the negative KT power, should really only be, half of our original amount, right? Okay? And so what we're going to do is we're going to solve this out, okay? Right? So we're going to say, okay, the first thing I'm going to do is I'm going to say both of them have a y0 in it. So I'm going to divide both by y0. Those cancel out, those cancel out. And we find that e to the negative KT power is going to be 1/2. Now, you guys probably haven't done a lot of these radioactive decay problems, but you'll figure out that this kind of happens all the time. So we want to basically solve this out for K is what for T. That's what I'm trying to figure out, okay? So what I do here, if we want to get rid of E, okay, we have to take the natural log of both sides, right? Natural log of both sides. Natural log and E cancel each other out, and I say that negative KT is equal to the natural log of 1/2, okay? Now, you may know this or you may not, right? But if we want to solve this for T, I'm going to divide by negative K on both sides, right? Those two cancel out. And I find that T is equal to All right, ln of 1/2 is really ln of 1 minus ln of 2 all over negative k, right? And so you'd actually know that ln of 1 is really just 0, right? So that's actually 0. Our negatives are going to both become positive, and we find that t is actually equal to just the ln of 2 over k. Okay? And so, again, you'll find out that half-life really only depends on k itself, right? Because t is really just ln of 2 over k. And so what that means is that anytime we're looking for something, right, we can just worry about what k is to figure out what our t is. And so this actually gives us our definition of half-life. So half-life, here's our definition. Okay, our definition is this. Half-life equals to ln of 2 over k. Okay, where k is our rate of decay, basically, right? So we get that. So hopefully this helped you out. Hopefully you're not too confused after all of this. And we'll be able to move on to video number 2.